Many of the traversals that we focus on walk around the graph, calculate some statistical values, select a list of vertices or edges, pick a value, or something like that. But the subgraph traversal extracts a full subset of the larger graph for analysis, visualization, or some other purpose. Specifically, it generates an edge-induced subgraph based on the edges we give it in the traversal stream. Now, an edge-induced subgraph is a subgraph formed by the subset of edges and their endpoint vertices. In a graph, it doesn't make sense for an edge not to have a vertex. Therefore, once we have an edge, we also have the vertices it is connected to. Also, all of the properties from the vertices and edges are copied into the subgraph. So the subgraph would have all of the properties we would expect it to have. For subgraphs, we have a new step. That step is subgraph. We give it a label, and this label is the name of the induced subgraph. This generates an edge-induced subgraph from the edges it receives in the traversal stream. Now, this subgraph is not passed on to the subsequent steps in the stream. Instead, it is produced as a side effect. That is why the label is so important. That is how we're going to identify it. It is sort of stored off to the side in a map, if you will. Its label is the key, and the subgraph itself is the object in the side effect map. Now, we mentioned that the subgraph step doesn't pass the subgraph into the subsequent steps in the traversal, but you can force that if you would like. If you use the cap step, you tell it the label of the subgraph of interest. If you use the cap step and you tell it the label of the subgraph of interest, what cap will do is force all of the traversers that you have defined so far to complete their work, that is, to completely define the subgraph, and then pass that subgraph onto the next step in the traversal. Or, if you don't want to pass the subgraph onto the other steps in the traversal, you can just call iterate. Now, iterate will also, like cap, force all of the traversers to do their work. So you will know that when iterate is done, the subgraph has been completely computed. But the subgraph will just be stored into the side effect area and not passed on to the subsequent steps in the traversal. For our upcoming examples, a reminder, as always, of our killer video movie schema. Users know other users, users rate movies, and movies belong to genres. We also have people who act, direct, write, or compose the movies in our killer video sample data. For the upcoming examples, it's important to remember that users rate movies and users know each other. That's the part of the example data that we're going to be extracting for our traversals. In this first example, let's extract the complete social graph of all killer video users in our example data. This graph will be the users who know other users. In the traversal, we begin with our graph and we look at all of its edges, and then only those edges which have the label knows. We know from our schema that those edges will be connecting our users. Then we ask for the subgraph and we give it the label socialGraph. After this, we cap the social graph, which means we make sure all of the traversers run and pass those traversers on to the next step in the traversal. Then we call next, which will access the actual subgraph object that we have computed. And that is what we're going to return. That is what this traversal returns into the identifier socialGraph. Then we create a new traversal on that subgraph, and we're going to do two things to it. First, we will get all of the vertices and group count them. Group count is a statistical step that we went over in a different video. It is going to find all of the vertices that have a common label, as shown in the by modulator. We will group up the vertices by their label and count them. But in this subgraph, we only extracted users, so we're going to find 1,079 users. Next, we'll do the same thing, but with the edges. We will group them by their label and count them up. Now, this is our social graph, so the only kind of edges that we're going to see has the nose label. Lastly, because this is an edge-induced subgraph, there is a consequence. We will never see vertices that do not have edges. It is perfectly fine for there to be an isolate or disconnected vertex in our graph. A property graph supports this idea, but those vertices will not show up in our edge-induced subgraph. And this last traversal counts up the total number of isolate vertices. In this traversal, we are looking for all of the vertices labeled user, but do not have a nose edge coming in or out. We count them up, and we have 21 of them. That is, we have 21 disconnected users or loner users who do not know anyone in our dataset yet. Next, let's find a subgraph based on the immediate social connections of a particular user. That user, in this case, is going to be good old U1. So we are going to look for the vertex that has the user ID of U1. Then we're going to get both the incoming and outgoing edges with the nose labels. That's all the social relationships for this user, and compute the subgraph. That's all the social relationships for this user, and compute the subgraph based on those edges. In edge-induced subgraphs, we start with the edges. We will call that the U1 graph. We will cap it to force those traversers to do their work, and then we'll return the graph. We will do the same kind of statistical analysis on this graph as we did in the last example. We're going to group count by label, the vertices, and the edges. In the results of this traversal, we see that we get 6 users. Of course, they're only going to be users because of our social network schema. We know that this edge only connects users. Keeping in mind, this will be the original U1 plus 5 other people that U1 knows. Then, we will count the edges by label and find that we have 5 of them, the U1 vertex, and 5 edges to the 5 people that U1 knows. Let's expand our search a little bit. Let's look at the friends of U1's friends. To do this, we will need to use a recursive traversal. That is covered in a whole other topic, but that is the repeat step on the second line. To start, we get user U1, and then we do a recursive traversal looking for both incoming and outgoing edges, looking for the nose edge label, and we compute the subgraph based on those edges. Now, note that the subgraph step is included inside the repeat step. So we are repeating that. We are repeating the subgraph step. And each time we give it the same label, U1 graph 3. How many times are we going to do this? You see that in the 4th line with the time step, where we say to do this 3 times. So as the traversal is repeated, the state of that side effect object, the U1 graph 3 object, is changed as the repetition proceeds. As we run this traversal, U1 graph 3 is growing as a subgraph. When we are done, we cap it to make sure those traversals are doing their work, and we get the graph back in the U1 graph 3 identifier that we specify in the top line. Then we do the same statistical analysis. We group the vertices by their label and the edges by their label. We see that there are 195 users. That is 1 user for U1, and then 194 friends, friends of their friends, and friends of their friends. And then 240 edges that connect all of the people in this increasingly large subgraph. Now, a subgraph traversal does not have to be limited to only extracting one subgraph. In this example, we are going to extract 2. We are going to start with all users and get the edges that connect them. That is, get all of the nose edges in the graph. This is kind of the whole social network. Then we extract that subgraph, calling it socialGraph. Now, when we are done with that subgraph step, we call both V. Now remember, subgraph doesn't pass the subgraph on to the next step in the traversal stream. It generates a side effect. So the both V call on the second line is taking its input from the both E on the first line. Now in our schema, the endpoint of a nose edge is always a user. So both E will give us user vertices. From there, we will look at outgoing edges that have the rated label, and we know from our schema that those are going to be the movies. So we'll get the subgraph of movies. So now we have created a side effect called movie graph on the 3rd line with that subgraph of movies. From there, recall that we are on an edge. The most recent step and relevant step was out E, rated. So we're going to go to the incoming vertex with the in-V call. Again, we are at movies. We will go from there to the outgoing edges, and in our schema, we know that those outgoing edges coming from movies are to things like director, actor, belongs to, and so forth. So we already have a subgraph called movie graph. So in effect, we are adding stuff into that graph by using the same label again. So we are kind of enriching our movies subgraph with all of the people and genres associated with the movies. Then we want to do things with those 2 subgraphs. So we can cap them both. We call cap, and we ask for the socialGraph and movie graph labels. Those traversers will finish, and we will return those subgraphs in the graph identifiers that we have named on the first line. Now, the object graphs will be a map of 2 subgraphs, socialGraph and movie graph. We will define traversals on those, and again, do very similar analysis. We see the vertex and edge statistics of the socialGraph. There are 179 users and 3,500 relationships relating those users. We see the vertex and edge statistics of the socialGraph. As expected, there are 1,079 users and 3,500 relationships relating those users. Then we see the label distribution of the movie graph. There are 920 movies, 8,759 people, 18 genres, and of course, those 1,079 users who are rating them. Likewise, we can count the number of edges relating those things, and we can get interesting facts, like that there are 1,668 screenwriters or 1,061 directors in our database. Now, it's worth noting, if we were to merge these 2 subgraphs back into one, we actually wouldn't have our original graph because we have lost the disconnected people. We extracted the socialGraph, and the users with no social relationships didn't have a chance to show up. We lost them, and we also lost their ratings. So the fact that we are extracting edge-induced subgraphs has consequences like that. And here's one more way of doing the same thing. Now, our subgraph definitions are exactly the same as the previous example. We are getting the social graph and then the movie graph. We get the movie graph by starting with the movies, the people that have rated them, and we add onto that people who make the movies, the genres they belong to, etc. Instead of calling cap, we just call iterate. That is it. The traversers do their work and the traversal is done. Now, to access the subgraph, we have to look at the side effect collection. We treat it like a map, and we get these things out of it by label. We get the social graph and the movie graph, and we create new traversals on those things. Then, the rest of our analysis is exactly the same as before. The key point in this last example is the side effect map and how to use that. When we make a subgraph, we are creating a side effect. We are putting an entry into this side effect map, whose key is the subgraphLabel, and the value is the subgraph object itself. We have this simple API that you can use to access those. That is subgraph traversals in a nutshell. We hope these examples have been helpful as you dig into the following exercise.